Hello students, welcome to the 38th lecture on particle physics. We are going to discuss today relic neutrinos, and these are the relics of the Big Bang, as we believe that this universe has come into the existence when a huge explosion took place, and at that point the temperature was more than 10 power 40 degree Kelvin, and everything started from a singularity, and after that the universe expanded. Now at that point we had radiations, and slowly after cooling, those radiations gave rise to particle, antiparticle, and gradually the atom and then molecules, etc., were formed. Now, what we know about relic neutrinos is that in every cubic foot of space in the universe, there are around 10 power 7 neutrinos. That means more than 10 million neutrinos, which were created in the Big Bang and are still zooming around. This is something similar to what we believe in cosmic microwave background radiation. Those are the photons which got disentangled from the universe, and they are spread all around the universe, and they were observed for the first time by Penzias and Wilson. Similarly, it is believed that these neutrinos, they got decoupled from the matter and they exist in this universe. Now, what I am talking about is the age of the universe. Presently, we believe that the universe is almost 14 billion years old, and everything started from the Big Bang, and then we had exponential growth, and what we find out that gradually we had radiations, then these coagulon plasma, then we talk about the formation of atoms, finally formation of molecules and other things. Therefore, the stars, the galaxies, etc., are much later development. Therefore, what are relic neutrinos? They are a cosmic background of neutrinos decoupled about 1 second after the Big Bang. Now, they decoupled from thermal soup when the temperature of universe became 2.5 million electron volt. And we know that if we have E equal to kT, this is Boltzmann constant, which is 10 power 23 in SI units. This is the temperature in Kelvin. Then with 2.5 million electron volts, that means 10 power 6 into 1 for electron volt and 1.6 into 10 power minus 19 joules, we can estimate what was the temperature at that point. Presently, we believe that there are 330 neutrinos per centimeter cube. Therefore, the density of these neutrinos are around 330 neutrinos per centimeter cube, and energy of these neutrinos are 0.4 milli electron volt. Milli is 10 power minus 3, 0.4 milli electron volt, and that is why it's very, very difficult to detect. They are very low energy particles. As we know that it's already very difficult to detect neutrinos, and then they are very, very low energy neutrinos, and that is why efforts are going on. People are looking for the bolometric type of detectors, and they are planning to detect relic neutrinos. And this relic is the relic of the Big Bang. Therefore, like we have the relic as the cosmic microwave background radiation, these are also the relic of the Big Bang. And as you can recall, that cosmic microwave background radiation, the density of the photons are 400 photons per centimeter cube, while here we are talking about neutrinos density to be of the order of 300 neutrinos per centimeter cube. That is why once I told in this class that neutrinos are the most abundant particle after photons. Now, if you talk about protons and other particles, they are much smaller in number. Now, I am going to discuss a very interesting topic. When we look at the periodic table, what I had told you that hydrogen and helium major portion, they were formed during the Big Bang, and then after helium up to whatever elements that you know, except for the transuranic elements which you can create in the laboratory, all the elements origin is inside the star's core in the different phases, either when you have carbon forming or oxygen forming or up to iron, or then you have the other nuclei, or when a supernova neutrino burst takes place, then the neutrino wind, they give rise to the formation of heavier elements. Therefore, I am going to tell you about, in brief, about the formation of these elements and how the neutrinos are important in the formation of these elements. Therefore, what I am concerned with, I am talking about, I have divided this creation of nuclei into three broad groups. One is Big Bang nucleosynthesis, where we have hydrogen, helium, and traces of lithium. Then stellar nucleosynthesis, the core of the star, where we have carbon to iron. And then we have supernova nucleosynthesis, where we have elements heavier than iron. Now, what we know that everything started almost 13.7 billion years ago, when a big explosion, gigantic explosion took place. And the Big Bang theory states that in the beginning, the universe was all in one place. All of its matter and energy was compressed into an infinitely small point. That is what we call as singularity, and then it exploded. Now, from 0 second to 10 power minus 43 seconds, we don't have much knowledge about it. Therefore, we start from describing the universe after 10 power minus 43 seconds, which we call by the name Planck's time. At that time, the size of the universe was 10 power minus 33 centimeter, and the temperature was about 10 power 32 Kelvin. Therefore, the Planck's epoch is the time during which physics is assumed to have been dominated by quantum effects of gravity. Then, from 10 power minus 43 seconds to 10 power minus 36 seconds, universe size increased from 10 power minus 33 centimeter to 10 power minus 27 centimeters. Gravity got separated from the other fundamental forces, and the earliest elementary particles and antiparticles were created. Therefore, at this point, the very first bullet that I am showing you, all the four interactions, the gravitational, electromagnetic, strong and weak, they were one. And then gradually with time, when the universe started expanding, these interactions got decoupled. And that is why we need a theory to understand all these four interactions at one footing. As you can recall, we can unify electromagnetic and weak interaction. That is what was done by Weinberg, Abdus Salam, and Glashow. That is known as Glashow-Salam-Weinberg theory of electro-weak interactions, which predicted the existence of Higgs boson and other things which were found at LHC, Large Hadron Collider, in 2012. And we know that these Higgs bosons are the quanta of Higgs field, and all the particles get mass through the interaction of Higgs field. Therefore, Higgs field plays a very important role. Now, similarly here, the people are trying to move towards higher energy. As you can see that at LHC, we have the energy of around 14 trillion electron volts. 14 trillion electron volts, if you again convert into energy by using this formula, you will find that it is much smaller than what was the temperature even during 10 power minus 36 seconds, when the universe was 10 power minus 30 seconds old. Therefore, this cannot be achieved in one fine morning. Gradually, you have to move from 10 power 15 Kelvin to 10 power 18 Kelvin to 10 power 22 Kelvin, and for that you have to build very large accelerators, and that requires lots of money. Then from 10 power minus 36 seconds to 10 power minus 32 seconds, the universe expanded from a size of 10 power minus 27 centimeter to about 10 centimeter. Now this time, the strong force got separated and the universe undergone a rapid exponential expansion, as you can see, from 10 power minus 27 centimeter to 10 centimeter. A huge expansion took place during this time, and this is known by the name cosmic inflation. Then from 10 power minus 32 seconds to 10 power minus 12 seconds, electroweak interactions created large number of exotic particles, including W and Z bosons as well as Higgs boson. Now from picosecond to microsecond old universe, quarks, anti-quarks, electrons, positrons, neutrinos and antineutrinos with masses came into existence. The temperature was below 10 power 15 degree Kelvin. Therefore, all these fundamental particles which we have talked about earlier in the earlier classes, they were formed during this time. Quarks and anti-quarks, being particle and anti-particle, they got annihilated, but a surplus of quarks, about 1 for every billion pairs, survived, and that is what we call it by the name baryogenesis. We have already discussed in this class what is matter-antimatter symmetry. Therefore, what happened that we had equal number of quarks and anti-quarks to start with, but annihilation took place, and because of a phenomena known by the name baryogenesis, we have more quarks than anti-quarks, and we have almost 1 for every billion pairs. Then from a microsecond old universe to 1 second, quarks combine to form hadrons. That means the existence of protons and neutrons took place. Here the temperature was 10 power 13 degree Kelvin. Then further, during this time, as we approach towards the 1 second old universe, the electrons fused with protons to form neutrons and gave off neutrinos, which continues to travel freely through space, because neutrinos are weakly interacting particle. They are freely moving in space. Some neutrons and neutrinos recombined into proton and electron pair. The density of the universe at this 1 millisecond old universe, as we have taken mid value, was around 10 power 11 gram per centimeter cube. And the current density of the universe is 10 power minus 29 gram per centimeter cube. Therefore, we had started from an infinitely dense universe when the temperature was more than 10 power 40 degree Kelvin. It all started from singularity, and then when the universe was about 1 millisecond old, the density of the universe became 10 power 11 gram per centimeter cube. But this is still a huge number in comparison to the current density of the universe, which is around 10 to the power minus 29 gram per centimeter cube. Now, from 1 second to 3 minutes, leptons and anti-leptons dominated the mass of the universe, and these electrons and positrons, that means leptons, the electron, anti-lepton, positron, they annihilated to give rise to radiations, that means photons, and energy in the forms of photons freed up, and colliding photons again created electron positron pair. Therefore, electron in the left hand side, you can see that electron positron pairs, they got annihilated to give out radiations, and these energies were still so large that photons also gave rise to back to particle pair production. Therefore, you had electron positron creation. Now, from 3 minutes to 20 minutes, the temperature of universe fell to 10 power 9 degree Kelvin, and here atomic nuclei began to form through nuclear fusion process. Simple elements like hydrogen, helium, lithium, very small number of lithium, were formed. Therefore, we had proton and neutron. Then when the cooling take place, this proton and neutron started to combine themselves, and that formed helium and different isotopes of helium nuclei. And after about 20 minutes, nuclear fusion stopped as the temperature and density of the universe fell. Therefore, what we are talking about, that we had proton and neutron that combined to give us deuterium, and deuterium and proton give rise to helium-3, and all that, as you can see, we are talking about helium, lithium, and in this process also we are creating helium. Therefore, we have hydrogen, we have helium, and we have lithium from Big Bang nucleosynthesis. Now the story becomes very interesting. This becomes interesting because the question arises, if we had only this much from the Big Bang nucleosynthesis, then from where the other matter came into existence? For example, if this is the drinking water, and if I ask you the question, from where you have got hydrogen and oxygen atoms, then the answer to that is the hydrogen atom inside this water is the relic of the Big Bang, because this is the hydrogen atom which was created more than 13 billion years ago, and the oxygen atoms, where there are trillions of oxygen atoms, they were created in the different cores of the stars, and during the explosion those atoms came out and gave rise to such beautiful thing. Therefore, the important point is we must try to understand them. Now, first one should understand how the stars came into existence. And the reason of their existence is nothing but the interstellar matter. What is interstellar matter? When we look at the sky, to the stars, they and their ancestors, they are the reason of the existence of their elements, and the space between the stars is not empty. Those are filled with interstellar matter. And these interstellar matter, the main constituent is proton, followed by alpha particle, and very small traces of heavier nuclei. Therefore, it is all hydrogen, a small fraction of helium, and very small amount of heavier nuclei. And these are distributed in space, but their distribution in space is not uniform. If I say that these are interstellar matter between the stars, then their distribution in space is not uniform. For example, generally we say that the density of these interstellar matter is 10 power minus 24 gram per centimeter cube. But there are places where the densities are million times more than this average density. And those are known by the name, they are interstellar clouds, they are known by the name nebulas. You have various nebula which have been observed in the different experiments using telescopes like Hubble telescope and others. And these nebulas are again places which are very huge, and then inside that nebula there are places where the density is larger than, suppose I am talking about this nebula, then there are places where the density is larger, much larger than, 1,000 times larger than the average density of the nebula. And these are known as globules. And these globules are the reason for the existence of the stars. Now, how does that happen? This happens because of three reasons, or this may happen because of three reasons. These are again theoretical concept. One is during star formation, star releases lots of matter in space, and these matter travels with a high speed, and they disturb this part where the density is large, which I am calling it by the name globules. Now, when I am telling you that these globules are relatively denser places where we have mainly protons, that means there will be gas pressure. Now, if some disturbance is passing through it, then either the gas pressure will overcome this disturbance, or if the disturbance will dominate, then there will be certain place in this globule where the density will become larger than the average density of this globule. And that means here the mass will become higher in comparison to the mass in the vicinity of this region. Now, from Newton's law of gravitation, we know that if we have a higher mass object and a lighter mass object, then this will get attracted towards it. Therefore, the lighter mass objects, the protons which are surrounding to this globule, they start coming to this. They start coming to this region where the density is high, and they start coming to this region. As they gradually approach, their kinetic energy increases, and when they struck this part, they impart their kinetic energy to this in the form of the thermal energy. Therefore, gradually the temperature of this region starts increasing, and it takes millions of years to reach a temperature where nuclear fusion reaction inside that very small part starts taking place, and there we say that a star is born. Therefore, this star is known by the name protostar, that is getting formed, and then a nuclear fusion starts taking place. Once the nuclear fusion starts taking place, then we say that the star has come in the has become a main sequence star that we discussed in the lecture where we were talking about the different spectral classification of stars. Now, depending upon the mass of this part, the fate of the stars get decided, and the most important point is that when we have the existence of this star gradually expands, because when you have nuclear fusion reaction going on inside the core, the temperature, the radiations starts coming out, and these radiations expand the envelope of the star, and this is how the different layers of a star gets born, which we discussed on the last turn as photosphere, chromosphere and corona in the case of sun. Therefore, these are the different atmosphere of the sun which arises because at the core the nuclear fusion has started taking place, and then you have the surrounding material where the radiations are coming out, and these radiations are expanding that atmosphere of the star, and then you have the different dense medium in the vicinity of that core of the star. But as you go far from that core, the gravitational pull will become weaker, and therefore if the matter is at very large distance, then that will not be able to control, the gravitational pull will not be able to control those matter. But this is not a well-defined place, and that is what I had told you, that the outermost layer of the sun, which we call by the name corona almost extends to the earth. It is not a well-defined region, but the temperature of that region is very high. Therefore, let's stop here. From here, in the next lecture, we shall talk about the other courses of stars and how neutrinos play an important role in the formation of elements. Thank you very much.